Hello, I'm going to talk about nuclear cooling. Previously, I've talked about how you can use magnetic cooling using a paramagnetic sword to achieve a cooling effect by magnetizing and then demagnetizing the sword. And now using magnetic cooling, temperatures of all the way down to the microkelvins has been achieved. But using paramagnetic sword, however, this is not possible. The reason is that paramagnetic sword has a Curie temperature of about a few millikelvin. And once the temperature goes down below the Curie temperature, the nature of the magnetic material becomes ferromagnetic, and then all the dipoles align and it doesn't work. Now, so what we need is a material whose Curie temperature is of the order of the microkelvins or less if we want to cool down, if we want to use this magnetic cooling method to cool down to the microkelvin. So let's think about this limitation a bit. The limitation due to the Curie temperature has to do with magnetic fields from the atoms themselves aligning each other. So let's look at this picture again. For material, atoms in the material, and each atom in a magnetic material has a magnetic moment. So each atom is like a tiny magnet, and this tiny magnet will align itself to a magnetic field, and that magnetic field can come from outside. If you bring a magnet close to this material, many of the little magnets would align themselves along the magnetic field. For each of these atoms, the magnetic field that it feels can also come from the surrounding magnets. So can come from the surrounding atoms, because those atoms are also tiny magnets. So there is this surrounding field from the magnets around it. I'll call the resultant, the combined effect, B. So this atom itself would have a certain magnetic moment, mu. Okay. So the Curie temperature is a temperature below which this field will be strong enough for the atoms to align themselves. Okay, because temperature gives rise to the thermal motion, which disturbs the atom. Okay, but if this thermal motion is reduced, the atom will be able to align themselves under the influence of the surrounding field. And because of this connection, as I've explained previously, mu B, the energy, the magnetic energy due to the surrounding field on an atom, is of the same order as kBT, the average kinetic energy of the atoms due to the temperature. The T is Tc, the Curie temperature. So the temperature at which the thermal motion can just overcome the magnetic field, hence the equation, the relation, right? Okay, and from that we obtain a connection between the surrounding field and the Curie temperature, And as I mentioned, the Curie temperature gives you the lower limit for magnetic cooling for a particular material. Okay, and for the paramagnetic salt, that was of the order of the millikelvin. Now, in order to go all the way down to the microkelvin, we have to use a material whose residual field is a lot smaller. Okay, so in the case of paramagnetic salts, the field comes from the electrons around the atoms. So each electron has a magnetic moment, so the electrons act like a tiny magnet. Now an atom has lots of electrons around it, and most of them will arrange themselves so that the fields cancel. You have spin up and spin down for each energy state. So most of them would cancel except for maybe a small number of electrons, which would give a resultant field. So in a paramagnetic salt, the magnetic moment is due to the electrons. Now the way to achieve much lower temperature is to make use of the magnetic moments of the nuclei of the atoms. Now in a nucleus, the protons, neutrons also have magnetic moments. So these also act like tiny magnets. But the magnetic field is a lot weaker, and magnetic moment is a lot weaker than that of an electron. Now to see how much smaller it is, for electrons, the magnetic moment is roughly of the order of the Bohr magneton which has this value of the order of 10 to the minus 24 joule per Tesla. Now for a proton, for example, the magnetic moment is of the order of mu n. That's the nuclear magneton, and that is of the order of 5.0510 to the minus 27 joule per Tesla. So this is about 2,000 times smaller. Now if you think about this nuclear magneton, suppose that if I want to make use of the magnetic moment of the nuclei, what I have to do is I have to choose a material whose magnetic effect of the electrons are zero. In other words, I must, for example, have electrons that are all spin up and spin down that are all paired up, all right, in the atoms, so that the magnetic moments due to the electrons in the atoms add up to zero, so that the only magnetic effect comes from the nuclei. And one common example which is used for this so-called nuclear cooling method is copper. So copper is often used for nuclear cooling, and it makes use of the nuclear magnetic moment of the copper atoms. Now, and as I said, the size of the magnetic moment in the nucleus is of this order. Now if you compare it with the magnetic moment due to an electron, is about 2,000 times smaller. And what that means is that if you look at a particular copper atom, for example, its own magnetic moment is of this order, okay, 2000 times smaller, and the surrounding field, the field from the surrounding atoms acting on one atom, the B there, is also about 2000 times smaller. So you have here, that becomes 2000 times smaller, that becomes 2000 times smaller. Multiply that together, that is a lot smaller. That is like 4 million times smaller. So you would expect a Curie temperature which is much, much lower, right? Maybe not as much as 4 million times, but many orders of magnitudes lower than the paramagnetic sort. So this means that using the nuclear magnetic moment for cooling, we should be the Curie temperature should not be a limitation if you want to go down to the microkelvin. Okay, so this gives us a way to go down to the microkelvin. Now, having established this possibility, I'll just mention some practical issues when using nuclear cooling. Now, there's one nice thing about using copper is that it has very good thermal conductivity, so it really helps to conduct away the heat more efficiently than if you are using a paramagnetic salt, which is not a metal. Now, the other thing is that if you're going to cool down all the way to the microkelvin, there are practical issues, because in practice, in such very low temperature setup, it takes a very long time to cool down, because the closer you get to 0 Kelvin, the more time it takes to remove a little bit of heat. And in order to help to speed up the cooling effect, there are a few things that has to be done to speed it up. And one example of this is that, if you remember, in the case of the paramagnetic salt, previously I've said that we could start from roughly, we can say, the liquid helium temperature, and then when you do the magnetization and demagnetization, you could bring down the temperature of the paramagnetic salt to a few millikelvins. So there's this idea that you have to start from somewhere. You don't just start from room temperature. That would be a long way to go down. Now, in the case of nuclear cooling, likewise, it would be very slow, maybe too slow, to actually start from liquid helium temperature. So in nuclear cooling experiments, typically the experiment would start from the millikelvins. So that means that the experiment wouldn't make use of a liquid helium bath as a starting point for nuclear cooling. It would perhaps put this block of copper into, say, a dilution refrigerator, right? And we have learned that a dilution refrigerator can take the temperature down to the millikelvins. So that would be a starting point. So starting from the millikelvin, this copper block would then take over and bring the temperature all the way down to the microkelvin. So there is this practical step of starting at a lower temperature to achieve the microkelvin. Now the other thing is that to help to speed up the cooling effect, there are a few things about the process that we can tweak. If you recall from the explanation about the cooling effect, we have in the beginning this material with all these atoms, and in the case of nuclear cooling, we are making use of the nuclear magnetic moment of the atoms. There are spin up and spin down. Okay, when the applied field is 0. Okay, so there's just some residual field there, and when an external field is applied, so we have a B, the level splits into minus mu B and mu B. Okay, and then when it splits, you have initially the same you have this initially the same number of particles in the higher and lower level, but particles would come down to follow the Boltzmann distribution. Okay, and in doing so, gives off heat. So that's the isothermal magnetization step. Let me write that down. Alright, where you turn up the magnetic field slowly to allow time for the heat to dissipate as electrons move down from the higher to the lower level. So we have this step. Now when the particles come down, we then carry out another step in which we demagnetize it, and so demagnetization brings the levels together because the energy of the level depends on B, the magnetic field. So if B decreases, then energy level decreases, come together. Now this step was called, what do I call it? I call it adiabatic demagnetization. Okay. Now, an adiabatic means that you don't allow heat to come in or go out. You assume that you can insulate it very well, and that means that because, for example, heat cannot go in and come out, the number of particles at the top level cannot increase or decrease. Likewise for the lower level. Okay, you have seen how when particles come down to the bottom, heat has to be given out. So if we have insulated it, no heat can go out, no heat can come in. So the number of particles at each level stay the same. And then because of the Boltzmann distribution, if the number of particles stay the same when the energy gap decreases, temperature must have fallen. Alright, because otherwise, if the temperature doesn't change, then when the energy level, then at lower energy level, we expect the number of particles to increase, to be more than that. But by forcing the number of particles to stay the same, we force the temperature to decrease. So that's the principle behind magnetic cooling. Okay, now when we use nuclear magnetic cooling, what difference does it make to this picture? So we have seen that the basic reason we can use nuclear cooling is that the magnetic moment of the nuclei is a lot smaller. So instead of the Bohr magneton, we had the nuclear magneton. It's about 2000 times smaller. And because the energy level is the magneton is this constant times the magnetic field, it means that if the nuclear magneton is 2000 times smaller, the energy spacing is also 2000 times smaller. That means this energy spacing is very close together. And that is not good, because if the energy spacing is very close together, the number of particles there, right, or not that many particles would come down to the lower level. Right? If the energy spacing is big, then that level is higher, so more particles will come down to the lower level. But if the energy spacing is small, only a small number of particles would come down. And that is not good, because, as we have seen from this picture here, alright, the number of particles on the top level compared to the lower level determines the temperature of this final system. Right? If you remember from Boltzmann distribution, we know that fewer particles at the top can also mean lower temperature. So in that sense, we know that the number of particles determine the temperature. So if you want a lower temperature, you want fewer particles at the top level. And if you want fewer particles at the top level, you want the spacing to be bigger. You want the top level to be higher. You want the top level to be higher. But because we are using the nuclear magnetic moment, the mu is very small, so the spacing is very small compared to using paramagnetic salt. And that means that not that many particles will come down to the lower level, so that the top level is not that much, there are not that much less particles in the top level compared to the bottom level, and that means that you don't achieve such a big drop in the temperature. Now, in principle, alright, we have seen that the temperature is limited by the residual field. The lowest temperature is limited by the residual field, and the Curie temperature by the residual field from surrounding atoms. So in principle, all we need is to remove the magnetic field, okay, and the external field, and the temperature should be able to drop until it's quite close to the lowest temperature. But as I've said, to go down to the microkelvin, that would take a long time if we start from a higher temperature. That's why it's better to start at the millikelvin. But even if we start from the millikelvin, because we are going towards such a low temperature, it still takes a long time and a lot of setup to insulate this properly to prevent heat from outside leaking in. So anything that can help to speed up the cooling, alright, would be useful. So in this case, because of this understanding that we can, that having fewer particles at the top helps to bring down the temperature. Therefore, anything that we can do to reduce the number of particles at the top level will help. And since, as we have seen, the problem comes because the mu here, the nuclear magnetic moment, is so much smaller than the paramagnetic salt. One way to make up for that is to try to use a bigger field. So typically for setups that are being used for nuclear magnetic cooling, the field would be of the order of 8 Tesla or maybe more these days. So that is a very high magnetic field. It's probably close to the limit of the present technology using superconducting magnet. But we're talking about an increase of maybe close to 10 times the magnetic field. That's also that's not that much compared with that drop of nearly 2,000 times in the nuclear magnetic moment. But at least that will help towards bringing down the particles at the top, and then eventually that helps to speed up the actual reaching of that low temperature. Okay, so that's the main the main ideas about nuclear magnetic cooling. The next thing I'm going to talk about is how to is some ways to estimate the heat energy that is given out during this cooling and how much heat will be absorbed as it warms up. I'll start with sketching a graph for the entropy against temperature of say a paramagnetic salt. Right. We've actually looked at this in one of the previous sessions. Now, if you recall, when we have a paramagnetic salt, each of the magnetic ion can, assuming a spin half salt, each of the magnetic ion can have 2 levels when it's in a magnetic field. Right? So if I want to think about the entropy curve, then at the very low temperature limit, all the magnetic ions are in the ground state. So there's only one possible arrangement, and therefore the entropy goes to zero at zero temperature. But at the high temperature limit, it becomes equally likely for the particles to be in either of the two energy levels, and that led to an entropy of n kb log 2, where n is the number of particles that have magnetic moments. So the curve looks like that. Now I've sketched this in log scale. Okay, so that's 0.1, that's 1, that's 10. That's in Kelvin. Okay, and let's say this curve refers to a magnetic field of 0.1 Tesla. Change that to 0.01 Tesla, right? Okay, now suppose that I now think of this material, this paramagnetic salt, in a higher magnetic field, say 0.1 Tesla. Now the corresponding curve would look like this. That's what it would look like. So it has moved to the right. Let's try and understand this physically. Why does it appear to move to the right? Now to do that, let me start with, say, a paramagnetic salt at 0.01 Tesla at a low magnetic field. And let me start at, say, a temperature of 1 Kelvin. So that means that I'm there. Okay, I'm at that point there. So starting from this, let's go through the magnetic cooling process. Let's start with the isothermal magnetization. So I will start applying a magnetic field to it, or you can imagine having an electromagnet around it and then turning up the currents. So the magnetic field increases, and as the magnetic field increases, recall what happens to the energy levels. The spacing between the levels increases, okay, and particles starts going from the top to the lower level. So as you get fewer particles at the top and more particles at the bottom, the entropy decreases. Now we understand why that's the case. Recall the graph at say at zero field that I described just now. When all the particles are at the lower level, the entropy is zero because there's only one arrangement. And when at very high temperature, the particles are equally likely to be in both levels. So you have the same number of particles at the higher and lower level. That's when the entropy is a maximum. So in between, if I start lowering the magnetic field, particles, the spacing starts to increase. As I start increasing the magnetic field, the spacing between the levels increase. So more particles come from the top level to the bottom level. Okay. So as you get more and more particles at the bottom level, the number of arrangements will decrease. Therefore, the entropy falls. Right? Now, the point would move along this vertical path because I'm doing isothermal magnetization, meaning I keep the temperature fixed. Right? So as the entropy drops, the temperature remains fixed. So that's why I can think of the point as moving down vertically. And eventually, as I turn up the field until 0.1 Tesla, it must reach a point on this 0.1 Tesla curve. So really, what has happened is that the entropy has dropped if I turn up the magnetic field. Okay, so if I start there, entropy will drop to there. If I start there, entropy drops to there. And that's why this curve looks like it has moved to the right. But really, we can also think of it as this part of the curve having come down. Alright, so that part is the isothermal magnetization. Alright, next we do the adiabatic demagnetization. Now when we do adiabatic demagnetization, we have seen that because no energy can go in and come up, the number of particles at each level stay the same as we demagnetize it, alright, as the levels come together. So, and because the number of particles at each level stay the same, so entropy stays the same. And we understand that from Boltzmann postulate because the number of arrangements would stay the same. So, but from classical thermodynamics, we also know that adiabatic processes means that entropy doesn't change. Okay. So, entropy doesn't change, but we know that the temperature falls. We have understood that. So therefore, starting from this point, the point will move horizontally to the left. Okay, horizontally because the entropy stays the same, and to the left because the temperature falls. And suppose that I demagnetize it until the field goes down to 0.01 Tesla. So it would reach this curve again. So having reached this point, the temperature would have fallen by some amount, so it would become cooler. So I have achieved the cooling effect. And then in a typical experiment, I would like to use this much colder, this cooled down paramagnetic salt to cool something, to cool some sample that I want to work with. Okay, so that's the cooled object. Then what next? Nothing, basically. If you remember what I've talked about for, say, the dilution cooling, remember how we achieve dilution cooling by having a layer of helium-3 on top and a dilute mixture of helium-3 at the bottom, and then as helium-3 diffuses downwards, we have a cooling effect. But we actually recycle the helium-3 by removing it from the bottom layer and then allowing it to vaporize and then cooling it and bringing it back. So we had this continuous flow process that was the dilution refrigerator. And that's also the kind of thing that happens in the refrigerator in your kitchen, for example. Right, the cooling agent there gets recycled over and over again as it vaporizes and gets compressed and gives out heat at the back of the fridge and so on and so on. So we have continuous cooling. And this is what we're used to. Unfortunately, it's not so easy to do continuous cooling using this method. So what happens is that once with this, I have this lump of paramagnetic salt or this block of copper. Once it is cooled down with this adiabatic demagnetization process, alright, once it's cooled down, there's no easy way to repeat the cycle. So what happens once it has reached that lowest temperature is that's it. So it's cold and you use it to cool down whatever thing you want to cool. And there's nothing much that happens except that heats will start leaking in because insulation is always imperfect. So we try to do the best insulation possible, but after maybe some days, heat will inevitably leak in slowly, and then the thing will start warming up, and eventually it will warm back up to the higher temperature where it started. Whether it is from a liquid helium bath or from a dilution refrigerator. So after it has warmed up back to the starting temperature, then it is no good anymore. It is not cold anymore. And then we have to start the process again to magnetize it and demagnetize it again. So quite troublesome. And this kind of cooling method is called a one-shot cooling method. So this is a one-shot method. Okay, as opposed to, say, the dilution refrigerator or your kitchen refrigerator, which is a continuous flow cooling method. Okay, now, and when I talked about dilution cooling, I talked about something called the cooling power. And the cooling power was the amount of heat it can remove every second. Alright, that's sort of the rate of cooling. Now, in this case, because there is not a continuous cooling happening, so this idea of cooling power, of rate of cooling, does not apply. But still, it is useful to have an idea of the cooling power. Right? For example, how do we tell whether one magnetic refrigerator, that's what we'll call it, how can we tell whether one magnetic refrigerator is better than another magnetic refrigerator? So we need to measure it using something that tells us how well it cools. Now this number, which we'll call the cooling power, is defined as the amount of heat once it has the material has cooled down to the lowest temperature, and then you just wait for it to stay there and warm up slowly. So from the point at the lowest temperature, the cooling power is defined as the amount of heat it will absorb, the total amount of heat that it will absorb as it warms back up to the starting temperature. So that's the cooling power. But how do we estimate this cooling power? Now we can actually do it from this graph. The formula to use is dq equals to Tds, a formula from thermodynamics relating entropy to heat. Now notice that to estimate this heat change, we need temperature and entropy. And it just so happens that we have a graph of entropy and temperature. So that's really convenient. But how do I get this TDS from the graph? Right. So first of all, think about the TDS. Think about it like when you do integration of a function. So if you do integration of a function, you think of this as like y dx, right? Okay, y dx. So you would think of, say, the t as the vertical axis, the s as the horizontal axis. Now, but in this case, we have the opposite. Instead of s being the horizontal, the x-axis, s is vertical. Right? T, instead of being the y-axis, t is horizontal. So this suggests that we should think of the t-axis as the vertical axis, the s-axis as the horizontal axis, and because we are interested in the heat change between this point, that's the coolest point, and the warmer point, okay, we want to integrate TDS, all right, from that point to that point. And if you're going to think of the s as the x-axis, that means that we want to find this area, all right, because that's what we find when we integrate a function. And that's our answer. The cooling power, which is defined as the heat absorbed as the material warms up along this path, is equal to the shaded area. So that's the answer. The shaded area is the cooling power. Alright. And while we are here, let's go back a bit and look at the isothermal magnetization as well. Now, if you remember, I said that as you magnetize it and the energy spacing increases, particles from the higher level will want to go down to the lower level, and then heat is given out. So during this isothermal magnetization, heat is given out. Now, this graph also gives us a way to estimate the total amount of heat given out during the magnetization. Can you guess what the answer is? It follows the same idea as this shaded area, except that this time, previously, the point follows this curve. Okay, so it is, and we think of the s-axis as the x-axis. So this is the area under the curve would be this area. Now this time, we're not following that curve, we are following this vertical line. So this vertical line is like our curve now. Alright, and we still have that as the x-axis. So therefore, the heat given out would be the area under this curve. I mean under as in this way. So it would be this. The rectangle. So the area of this rectangle here is the heat given out during isothermal magnetization. Okay, so one final point to make about the cooling power. Now I've talked about about paramagnetic salts, and I've talked about nuclear cooling using the nuclei of the copper block, for example. Now in terms of the cooling power, okay, for nuclear cooling, we'll be working at a much lower temperature than say using paramagnetic salts. So much lower temperature means that this part of the curve will be at a much lower temperature. So instead of say a few millikelvin sort of working temperature, this temperature will be much lower, alright, much lower. It would be in the microkelvin. So which means that this distance, we are talking about this area here being the cooling power. So this temperature here will be much smaller for nuclear cooling. And as far as this area is concerned, this horizontal length of this area will also be much smaller, and therefore the area here will be much smaller when we do nuclear cooling as a result. And that means that the cooling power for nuclear cooling is much smaller compared to when you use the paramagnetic salt. So because of this, nuclear cooling, although it can go down to the microkelvins, it has also comparatively and correspondingly smaller cooling power. Okay, we'll stop here.